So it's time we started working through some of the problems, and so this problem I'm going to do is problem 21.1 from the textbook, and that's Chapra Canale 6th edition. So we have the problem statement here that says evaluate the following integral, the integral from 0 to pi halves of 8 plus 4 cosine of x dx. Analytically, using a single application of the trapezoid rule, multiple application trapezoid rule with n equals 2 and 4, single application Simpson 1/3 rule, multiple application Simpson 1/3 rule with n equals 4, single application Simpson 3/8 rule, multiple application Simpson 3/8 rule with n equals 5, and it says for each of the numerical estimates b through g, determine the percent relative error based on a. So we're going to go ahead and start going through this. I think what we'll do is I'll just go through these one by one, and then we'll compute the percent relative error all at the end. To get started on part A, we can do this by hand, or we can go ahead and use a calculator. Your TI-89s can do this, and so I'm not going to bother doing it by hand, although it's a pretty easy problem. But I'll switch over to Wolfram Alpha and have that help us do it. So we just say let's make this big so we can see it. The integral from 0 to pi halves of, and let's see what it was, 8 plus 4 cosine x dx, of 8 plus 4 times the cosine of x dx. And let it think about the problem here, and we get an answer. Here it says, all right, the integral is 16.55 or 5664. It's exactly 4 times 1 plus 5. So 16.5664, and that is the answer to part A. For part B, we need to do a single application of the trapezoid rule. So first, what is the trapezoid rule? The trapezoid rule is just finding the area of the trapezoid. The formula for that is b minus a times f of x1, which is f of a in this case, because we have a single trapezoid, plus f of b divided by, or I should write it the same way, of x2 divided by 2. All right, so that will be then, just writing it out, that will be pi halves minus 0 times f at x1 and f at x1, so that will be evaluated at 0. The cosine of 0 is 1, and so that'll be 8 plus 4, so that's 12 plus f at x2, so that's 8 plus 4 times the cosine of pi halves, which is 0, so that'll be 8, all over 2, and so that will equal 20 pi over 4, which is going to equal 5 pi. And let's quickly get an approximation of 5 pi. That's not the one we want. MATLAB here. 5 times pi, 15.7. So for part 2, or part B, we get 15.7080. For part C, we're doing the multiple application trapezoid rule with n equals 2 and 4. And n in this case refers to the number of segments, and so we'll have 3 points and 5 points. So multiple application trapezoid rule, we could just write out the formula in the same way we've done before. We can also use MATLAB. MATLAB has a built-in function called trapz, and so the first thing we're going to need to do is set up our x and then our y and then do the trapezoid integration. So our x is going to go from 0 to 2 pi, or excuse me, not 2 pi, but pi halves. And it's going to go in step sizes of, we have to figure that out. Well, it's going to be the difference of pi halves minus 0, pi halves minus 0, and that'll be divided by the number of segments we want. So that's the whole interval divided into the number of segments we want. And the number of segments we want is 2, so we'll divide that by 2. And so then we get our x vector, and y is just equal to 8 plus cosine of x. If I remember right, let's double check that. 8 plus 4 times the cosine of x, 4 times cosine of x. So there we have our y, and so then we can say trap z x y, and we get 16.3586, and so that's I guess the first part of part C with n equals 2, but we also need to do it with n equals 4, and so we got to say x is equal to, I'm just going to get what we have, and instead of dividing it into 2 segments, we're going to divide it into 4 segments. And so we have that, and y is going to equal 4 times the cosine of x, and so we have to update it because we've changed our x, so we get all of them, and then we can do trap z x y, and we get 16.5148, and if we can see both of those at the same time, we've got 16.3586, so with n equals 2, here let's change colors. With n equals 2, we have 16.3586, and with n equals 4, we get 16.5148. All right, so that's part C. For part D, we have to do a single application of Simpsons 1/3 rule. And Simpson 1/3 rule is listed in the book on page 621. We just do b minus a times f of x naught plus 4f of x1 plus f of x2 all divided by 6. Now, we can, so instead of doing this by hand again, I'm going to use MATLAB. And so if we do use the same x's that we had, divide it into 2 segments, and we let our y's equal the same thing. Okay, so now we've got x1, x2, x3, y1, y2, y3, and so we can just plug in the Simpson 1/3 rule, and so we just say b minus a, that's going to be x3 minus x1, and that, we'll put in parentheses, x3 minus x1 times f of x naught, so we'll start a parentheses, f of x naught, so that's going to be y1 plus 4 times y2 plus y3, and that's all divided by 6. And we get 16.5755. Part E asks us to do the multiple application Simpsons 1/3 rule with n equals 4. N equals 4, we've used that before, and so let's just let's go back to MATLAB and find where we used n equals 4. X equals 0 to pi halves minus 0 over 4, that was the equation for the step size, to pi halves. Okay, so that gives us n equals 4, I believe. Let's see. 1, 2, 3, 4, 5 points. That's n equals 4. And then we can say y equals 8 times 4 cosine of x. Okay, so now we've got our x set up, and we've got our y. And the multiple application Simpsons 1/3 rule, we can just look that up. And the equation for that, and we can just say I then equals b minus a, so that'll be x 1, 2, 3, 4, 5, x5 minus x1. All right, so that's our b minus a times f of x naught, so that'll be so that will be y times y1 That's our first entry, so that's 12. y1 plus 4 times f at xi when I equals 1, 3, 5. That's since we're not using zero-based indices, that's going to be 2, 4, 6. But see, that's just then going to be 2 and 4 because we don't have 6. That'll be times y times y3, or excuse me, y2, plus 4 times y 4 plus 2 times y, and it'll be y3 plus y5. And that's all divided by 3 times n, and n in this case is 1, 2, 3, 4 segments. 3 times 4, and we'll put that here so we make sure we do it right. And so we get 16.5669. Part F asks us to do a single application of Simpsons 3/8 rule, and Simpsons 3/8 rule uses 4 points, and we can see this on page 621. And so Simpsons 3/8 rule uses 4 points, which means that we have 3 segments. So let's get MATLAB here and divide it into 3 segments. So let's say our x is equal to 0 from 0, and then and 3 segments to pi half, and y is equal to 8 plus 4 times the cosine of x. All right, so this should be good, and now we just apply the formula. So we get I equals b minus a, which is going to just be, yes, x. That will be x1, 2, 3, 4, x4 minus x1, and that's all going to be multiplied by, let's see, f of x naught. So that'll be y 1 plus 3 times y 2 plus 3 times y 3 plus y4, and all that divided by 8 gives us 16.5704. 16.5704. Now, on part G, it asks us to do a multiple application Simpsons rule with n equals 5. And now this is a little bit tricky because I'm not sure what they want us to do, because I mean we can't just use multiple application Simpsons 3/8 rule because that would require n equals 6. We can't just do multiple application Simpsons 1/3 rule because that would also require the different number of points. But what we can do, and perhaps this is what they're looking for, is we can put together an application of Simpsons 1/3 rule with an application of Simpsons 3/8 rule. Because if we do a single application of Simpsons 1/3 rule, that's going to be 2 segments, and a single application of Simpsons 3/8 rule, that's going to be 3 more segments for the 5 segments that they're asking for. And so let's go ahead and do it that way. Okay, so the thing is we have to think about this for a second when we do it. So the first thing is we can divide it into 5 segments, and that's easy enough. We've seen how to do that. Okay, here is 5 segments, and the first thing then is Simpsons 1/3 rule, and so so I'm going to call it I1, and then we'll just add I1 and I2 together. So I1 is going to equal our b minus a. Well, we're going to be going in this problem from 0 to 0.6283. So that will be, oh, and sorry, we have to find our y here too, or we can't do it. And so we're going to be going I2 equals then 0.6283. Well, that is just going to be x3 minus x1, and that's going to be then multiplied by, and now we're just going to do our Simpsons 1/3 rule, so that's going to be our y1, and we better start parentheses here, y1 plus 3, no, that's 4 times y2 plus y3 all over 6. And so that's our I called that I2. I don't know why I called it I2. I'll call the next one I3. And that's going to equal our interval we're integrating over, and so we're going to be going in this case, so we just went from 0 to 0.6283, now we're going to go from 0.6283 all the way to 1.5708, so that's going to be x 1, 2, 3, 4, 5, 6, x6 minus x3 times f at x naught. So the first point we're going to need is going to be this point. That's our y3. y3 plus 3 times y4 plus 3 times y5 plus y6, and that's all going to be divided by 8, and then we go I2 plus I3, and we get 16.5667. 16.5667. The last thing we need to do is show the error for the numerical estimates for B through G, percent relative error based on A. And so in order to do that, we sort of need to make a table. And so I've gone ahead and put all these values that we computed here from A all the way through G into this table. And so here it is. We have part A, B, C. We actually did 2 for C, one with n equals 2 and another one with n equals 4. And then we had part E, F, and G. So the thing we need to do then is compute the percent error, relative error, and that's epsilon sub t equals the true minus the estimate over the true value. And if we want it in a percent, we can multiply it by 100. All right, and so I've got an I here, so this I stands for the integral estimate. So I went ahead as well, and where's MATLAB? And I keyed them into MATLAB. So here's all the integrals, and I even included the first one in here because there's no reason why not. And so we're going to say the error then, let's call that E, equals our true, which is going to be 16.5664 minus the estimate, so we'll just say minus I, all over the true value, 16.5664. And then we'll multiply that by 100. And here we go. 5%, 1.25%, 1.3115%, 0.5, and we can do E equals absolute value. Well, it's usually absolute value we care about, but we can see what the sign is. That's fine. Um, uh, and that's it. So E equals abs E, and that's our error: 5%, 1.25%, 0.311, 0.05, and I'll go ahead and put that in the table, and we'll look at the results. All right, so here we have the final results of all these values filled in, and these are the percent error, and you see a few things here. First of all, the lowest error is on the two places. First of all, if we get more points, then we have lower error. The highest error was in our trapezoid rule, but when we had 2 points, we were good. When we had 4 points, we were a lot better off than when we had only 4 segments. We were a lot better off than when we only had 2 segments. But let's compare that to our 2 segment where we only had 2 segments here. We still had lower error when we were using Simpsons 1/3 rule than when we used the trapezoid rule. When we used the two applications of the Simpson 1/3 rule, we went ahead and cut our error in half. Simpson 3/8 rule, you can see it was really about the same amount of error as the Simpsons 1/3 rule, multiple application Simpsons 1/3 rule. It didn't really help us, but what did help us was when we upped it to 5 points, and we did the multiple application Simpsons rule using the Simpson 1/3 rule and Simpson 3/8 rule. That, of course, not surprisingly, gave us the lowest error.